But what we want to do today is start a new topic. Okay, strictly speaking, I should not really call this a beginning of our course according to the syllabus laid down, because the syllabus actually has this in the previous semester, but almost always it's impossible to cover all that in the previous semester. So for the last there's a third year I'm teaching this. All years I have essentially taught this at the beginning of the course. These are called the so-called approximation methods. Okay, so the last example that we had of these potentials which we cooked up from the wave function, they are actually pretty good introductions to this issue. As I said, even in those cases, you could find only one eigenfunction sort of exactly or analytically. In fact, you didn't find that eigenfunction. It was given to you. But after all, you can always cheat and say, okay, I've got this potential. Now I have this eigenfunction which I found out somehow exactly. Okay. But in those cases, almost none of the other energy eigenfunctions could be figured out analytically. And in most problems, even the one energy eigenfunction cannot be found out analytically. It has to be found out via approximation methods. Okay. Now, there's a bit of a problem here in language, especially if you want to read quantum chemistry textbooks, which some of you will definitely want to read, because quantum chemistry, of course, is one of the most important applications of quantum mechanics. You will often see references to exact energy eigenvalues and so on. Okay. Now, that is very confusing to hardcore physicists, because to us an exact solution is one for which you know the answer exactly. You have an analytical way of finding it out. To a quantum chemist, very often exact solution means you have some approximation scheme already laid down. Within that approximation scheme, you are doing an exact calculation. So your answer is not really exact in the sense that it's not an exact answer to the problem that was originally posed, but it's an exact answer to a truncated question which you have managed to solve. I will make this clearer later on when I talk of some real applications. So to us, exact will mean I have an analytic solution. So that's not what the quantum chemistry usage is. So in many textbooks, especially quantum chemistry textbooks, you will often see the word exact solution used in a different meaning from the one in which we are using it. Okay. But for the time being, sorry, what happened? Oh. Let me just point out that exact solutions are available only very, very rarely. So what we will do is we will have to rely on approximation methods quite a lot. And there are many, many different approximation methods. We will essentially study 3 of them. Okay, 3 is an approximate number right now. It could be more than 3. One is a variational method. The other, okay, let me be more precise than just a perturbation, because there are many different kinds of perturbation methods available. This one is Rayleigh-Schrodinger perturbation theory. That's the one which we are going to spend most of our time on. Although, let's just sort of lay the ground for other variants of the perturbation method. Some of them will just indicate, some we will do in slight detail. Another one, which is actually very, very important for many other reasons besides just exact solutions, is the so-called Jwkb method. The Jwkb method is, of course, named after 4 people. That's why 4 initials. Now, today we will start with are these the only possible methods for approximation? The answer is no, but these are the most common ones that are used. And we will need to be conversant with all of them, not only because they give you various nice approximation methods of solving energy eigenfunctions and eigenvalues in situations where exact solutions are not available, but also because sometimes they lead to other very important results. For example, many of you may have already heard of density functional theory, which is what well, which got us originated as a Nobel Prize in chemistry, because although it's a purely physics result, its use is primarily in treating theories of atoms and molecules. Used to be. Nowadays it's used in many other places. The density functional theory ultimately is based on the variational method. So it's sort of, and there are many other things, like you may have already heard of Hartree and Hartree-Fock methods for solving atomic problems. Even if you haven't heard of them, don't worry, you will. But basically all of those are based on the variational method in a way. So we will start with the variational method today. And we will use the variational method to solve for the ground state energy today of a system which will be a bit of an overkill. We will actually start by solving the ground state energy eigenvalue for the harmonic oscillator. As I said, complete overkill because we already know what the energy eigenvalue is and we know it exactly. Okay, but one good thing about trying to use your approximation methods on a problem for which you already know the answer is that it sort of gives you a confidence as to what kind of how good your approach is and what possible modifications you may have to make on it later on. Okay, so today, first topic, the variational method for finding out energy eigenvalues. And this is based on a very, okay, have you done this by the way already somewhere? Earlier course?
No, sir.
That's not been taught, right? Okay, fine. So let's start with this. Now the idea behind the variational method is very simple. The idea behind the variational method is this. Suppose you have a wave function which is normalized. Okay, I'm going to use position representation wave functions for most of the calculations in the perturbation in the variational part. However, it's of course perfectly legitimate to use the bracket notation for this. So let's say you have a normalized wave function and you calculate this expectation value. This is of course not an energy eigenvalue. This is just an expectation value for this particular state psi. And because this is not an energy eigenvalue for which I'm using the letter capital E, let's use the curly E for this. Now, what can you tell about the relationship between this and the energy eigenvalues of the system? Let's say the energy eigenvalues are E0, E1, E2, E3, and so on. Where E0, and they have been ordered. So E0 is the lowest energy, E1 is the next, E2 is the next, and so on. Suppose you have a situation like this, and you have a ground state energy E0. What can you say about a relationship between this particular expectation value and these quantities? Of course, E0, they will correspond to energy eigenfunctions, and I'm going to use phi, the letter phi or phi actually, to label the eigenfunction. So you have Ek eigenfunction, phi k. So these are the exact energy eigenfunctions. Okay, exact means they are there. We just may not know them. Anuruddha says it will be some linear combination of the eigenvalues. True, but can you be more specific? Okay, so let's start with this. We know, or I'm just going to use a bracket notation for the eigenfunctions as well. Vishayan already has given me the answer, but let me just see whether we can motivate that. So in general, the ket psi, or the wave function psi, you can just think of it that way, is some C0 psi 0, C0 phi 0 plus C1 phi 1, right? Or sum over k going from 0 to infinity and ck phi k. Now, just for the sake of convenience, I'm assuming that these energy eigenvalues are discretely spaced and they're countable. That is, I can label them using 0, 1, 2, 3, and so on. Even if we could not, even if there was a system, there are plenty of systems in which that can't be done. You may have a continuum of energy eigenvalues. Even for those, I'm going to just use this notation. Of course, this sum really does not mean a sum. It means sum over the discrete countable part and an integral with appropriate weights and measures over the continuous part. But for the time being, I'm pretty sure this is good enough for you to understand what we are saying. Any wave function can be expanded in terms of the energy eigenfunctions. That's the completeness theorem. And then if you calculate h psi h, I think it will be easier to see if I made the paper background plain. Okay, sorry. What did I write? I wrote something completely senseless. This is what I really wanted to calculate. Okay, so that's sum over k, ck star phi k bra. That's the bra psi. Then you have h. Then you have sum over l, el phi l. That's the ket. So that's, of course, once you expand this out, k and l, ck star cl. These are just complex numbers, so they will come out of this expectation value calculation anyway, and you get phi k h phi l. I hope everybody knows this, but I had to change the labels from k to l here simply because I do not want accidental matching of dummy indices, right? K and L are dummy indices. They have to be kept separate if you want two different sums to be accurately portrayed. So next step, use the fact that h phi l, we know this, that these are energy eigenstates. So h phi l is simply el phi l. So this is going to be el phi l. And el, of course, is an energy eigenvalue, so it can come out, it's just a number, so it can come out of this calculation, and you are left with phi k phi l overlap. And what is the overlap of phi k phi l? We are assuming that we have already orthonormalized the energy eigenfunctions. So and this is a result which all of you know, of course. In fact, you know this even for more than just the energy. Basically, you know that when you want to calculate the expectation value of any observable quantity in a given state, what you get is a weighted sum of its eigenvalues where the ck mod squares, which are give you the weights, and that really helps you to interpret ck mod square as a probability that if you were to measure the system in the state, measure this particular dynamical variable or observable quantity, ck mod square gives you the probability of finding the kth eigenvalue for that quantity. Right? This is something which you all know, I hope. So this is psi h psi in general. It is an it's a linear combination of the eigenvalues, but it's not just any arbitrary linear combination. What is important is psi h psi is a sort of average of ek, right? Because ck mod square, these are not arbitrary numbers, right? They are all non-negative numbers and they add up to 1. That they add up to 1 is simply normalization. Okay? Now this immediately tells you one thing. Even without going into mathematical tricky details, you should be able to tell me. If you have to average a bunch of numbers, what can you tell me about the size that the average can have? One absolute thing you can say about the average of a bunch of numbers, even if it's a weighted average with different weightings. Yes? Yeah, it has to be between the lowest and the highest with both ends included, right? Could be the lowest as well, or could be the highest, but would usually be somewhere in between. In this particular case, we have these numbers E0, E1, E2, E3, these energy eigenvalues, which are not bounded above for the time being. In most situations, you don't have an upper bound. You may, but in most situations, you don't. But you do have a lower bound. There's a ground state energy E0. Okay. If there is no lower bound to the energy, then the system will simply be unstable. And describing it using this kind of language would really be rather difficult and would lead to erroneous results anyway. So you're assuming that your energy levels are bounded below. There is a ground state energy. And this immediately tells me that this expectation value of psi h psi has to be greater than or equal to E0, where E0 is a ground state energy. Okay. Now, you may say what I said right now is not really very mathematically rigorous, so let's make it a bit more rigorous. All I'm saying is this is C0 mod square E0 plus C1 mod square E1 and so on, Ck mod square Ek and so on, and E0 is the lowest among E0, E1, E2, Ek. So if I were to replace every one of the EIs, every one of these, E0, E1, E2, E3, if I were to replace them all by E0, if I were to do this, one thing is sure, if I did this, the quantity here cannot go up, right? It can only go down. At best, it can stay the same. When can it stay the same? Yes? Remember, all these coefficients here are all positive numbers, right? That's important. That's why I'm insisting on this being a weighted average rather than just any linear combination. All these weight factors are positive. Yeah, it can stay the same as E0 only if all the other coefficients are 0. If I were to replace all the E1, E2, Eks by E0, the only way this can equal E0 is that C0 mod square is 1 and all the rest are 0. Otherwise, it's definitely going to go down. Anytime you change any one of the EIs to E0, note that if the coefficient here is not 0, let's say E1 is changed to E0, and if the coefficient here is not 0, it is positive. So you're actually bringing the sum down. But then this quantity is obviously just E0, right? This quantity is simply C0 mod square plus C1 mod square up to all the sum of all the coefficients summed together times E0. So this is just E0. So that's a more rigorous proof that this expectation value of H is bounded below by E0. If your system happened to have an upper bound to the energy eigenvalues, then psi h psi would also have been bounded above. But in most systems, it's actually bounded below and not above. Okay? So this is basically the result on which our, what am I writing? On which the variational principle is based. Take any normalized energy eigenfunction whatsoever, the expectation value of the Hamiltonian in that normalized eigenstate has to be equal to E0 or more than E0, cannot be less. Okay? Of course, if you did not bother normalizing this, even then you can still calculate this quantity. Remember, this is actually the expectation value for any normalizable state, right? You divide by the norm square. That's it. And this quantity in general has to be bounded below by E0. So this is the starting off point for the variational method. Any questions so far? No questions. Good. So that's good, assuming that it has been understood. That's why nobody has a question. Okay. Now let's go to how you would use this. This is of course a very standard and very simple theorem. So how would you use this? And let's try to figure out that result for our. Let's start with our well-known problem, the simple harmonic oscillator. The Hamiltonian here later on, or minus h cross square by twice l d2 dx2 plus half m omega square x square. Okay, later on what we will do is we will choose units in such a way that these nasty factors of h cross m omega etc. will go away. But for the time being, let's just keep everything in and try to do the work. Okay. Now, what we found out right now is that if I try to find out the expectation value of h in any wave state whatsoever, I am going to get a bound which is the ground state energy, or I will get more than that. So what I can do is I can start with a class of wave functions. Okay. All normalizable wave functions which are typically labeled by some parameter or parameters which we are free to vary. This will be clear the moment I start doing the problem. And then what I will do is I will find out the energy expectation value within that class of functions. Of course, that energy eigenfunction will depend on the parameter that I have used to label the system, label this class of wave functions. So now you have a function of maybe more than one parameter. Okay. So what is your next step? The next step would be, I would just try to, I know that no matter what value this parameter takes, the expectation value can never go below E0. So how can I get close to E0? I will just choose my parameter in such a way that this energy expectation value that I get as a function of these parameters takes the lowest possible value. That way, at least within this particular class of energy eigenfunctions that I have taken, I get to a very to get as close to E0 as possible staying within that wave function, that system. Okay, is that okay? Yes? Okay, let me just try to make this more precise by giving a concrete example. So let's take a family of wave functions. Remember the important thing in the variational method. At least when you want to use it for practical calculations of energy or practical estimations of energy eigenvalues, would be to start with a class of wave functions, not with a single wave function. So let's do that. Let's start with this wave function, this class of wave functions, which is an extra, in addition to being a function of x, there's an extra parameter here. Let's call that alpha. And what we will do is we will choose this. Or maybe I will make life a bit easier for myself by choosing it in this form. Okay? And there would be a constant in front, normalization constant. I've assumed that our wave function is normalized, or actually I will not. As I just explained a while ago, you don't need normalization. You have to divide by overlap of psi with psi. That you have to do. But you don't have to insist that your wave function starts out being normalized. Okay? So this is your psi x alpha. Now, if I were to find out expression value of h using this, will of course get a quantity which depends, of course, does not depend on x any longer, right? Because the expression value is calculated using an integral over x, but it will depend on the parameters which went into your wave function, so it will depend on alpha. So what am I supposed to do? I'm supposed to do this calculation. It is a minus x square by alpha square conjugate. Of course, in this case, this is a real quantity, so psi star psi will be psi. Okay, that's really wrong. Anyway, what I need to do is do this. Take its conjugate, then take the differential operator, Hamiltonian, then let that act again on e to the minus x square by alpha square. So that's the numerator. The denominator, of course, will be e to the minus infinity plus infinity to the minus 2 x square by alpha square dx. And you have to do this calculation. Once you do this calculation, I will tell you a trick which will help you do the calculation a bit more, help you do it a bit faster than usual. But anyway, in principle, this is all you have to do. Calculate the numerator, the denominator, you have take the ratio. Of course, this will depend on alpha in the end, right? Everybody with me so far? Yes, no? If everybody stays silent, I'm not even sure whether I'm connected. Okay, somebody has said yes, so I'm going to take that as a yes for everybody. Okay, now can anybody tell me one thing? If I were to minimize this E alpha with respect to alpha, what will the minimum value be? So Rahul is saying E0. Why? The variational principle only guarantees that the minimum value will not be less than E0. Hello. Okay, so my question to all of you. How are you so sure that you're going to get? Somebody said E0. E0, of course, we know the E0 for this system. E0 is. So the procedure, of course, would be I take this function alpha, differentiate it with respect to alpha, put this equal to 0, and this will give me a value alpha 0 for this parameter alpha. And what is being claimed is E alpha 0 will be half h plus omega. Are we sure of this? Because if you remember, all we said so far was the variational principle guarantees that you are going to get something which is bounded below by the ground state energy. So you should get half h cross omega or more. Apparently, you are claiming that we are going to get half h cross omega exactly. Yeah. Any answer to that? Okay, Sharon has given me the right answer, but anyway, I'm sure many of you could have guessed it. The point is, I have a family of solutions which we start with, right? It is a minus x square by alpha square. Why is this a family of solutions and not one solution? Because alpha can take many different values here, and depending on the value of alpha, you get different solutions. Okay, right? So, and you all happen to know in this particular case, of course, that's because we have chosen a problem for which we know the exact answer. You happen to know that the exact solution or for the ground state energy of the system happens to be a function of this form for a precise value of alpha, not for any arbitrary value of alpha, but for a precise value of alpha. Okay, right? Because of that, since we will get to, if we manage to get the minimum energy, which they, or minimum expectation value, sorry, for E alpha here, that minimum expectation value can only be for the exact energy eigenfunction that happens to be in this family, right? So there's no way you can go below that, but you will definitely get to that by choosing just the correct value of alpha. So this is a very unusual situation because we happen to know the exact energy eigenfunction here, and we have chosen a family which contains the exact energy eigenfunction. In most realistic situations where you will use this method, you will not know beforehand what the energy eigenfunction is exactly. So almost certainly you will not be this fortunate. But at least let's see what we can do about what we can get here. We know beforehand that if our method works at all, I will get the correct answer. But let's just try to see how this method would work. So what we want to do is calculate expression of H. This of course involves expression of the kinetic energy part and the potential energy part. So this is psi T psi, T being the kinetic energy P square by twice by psi psi. This is what we need to calculate, and this is of course psi V psi. Several calculations need to be done, but most of these are pretty straightforward standard calculations, which you should be able to do almost immediately. So, yeah. So what should we do here? Maybe just because of this presence of this extra 2 here, it might even be a good idea to define your original wave function with a 2 in the denominator. Okay, that's cheating, right? So I will not do that right now. But since we know that you are going to get e to the minus twice whatever is there anyway in the normalization calculation, it's usually a good idea to start by trying to keep as few of these unnecessary parameters as possible. So you would typically start with e to the minus x square by 2 alpha square, so e to the minus x square by alpha square. But it doesn't really matter. Okay, so how would you proceed with this? So if you just took root 2x by alpha to be z, it would be to the minus z square. By the way, I will come to that point soon, but let me just time being. The limits, of course, stay minus infinity to plus infinity for z as well as x. The dx here is root 2 by alpha times dz. So root 2 by alpha times this integral to the minus z square dz, which everybody knows how to calculate, I'm assuming. What's the answer? What is the answer to this integral? This is one integral which you have to know, by the way, by heart. The answer is root pi. This is the standard, one of the most standard integrals, standard non-trivial integrals that you have to do. So root over 2 pi by alpha. That's what the denominator is. Okay. Now for the psi T psi, or let's start the psi V psi first. Once again, the same substitutions, what did I do? Root 2x square by alpha square, minus 2x square by alpha square here. Same substitution, x equal root 2x by alpha is z. Of course, I could have avoided the root 2 simply by using a 1 by 2 alpha square in the wave function in the first place. But anyway, so x is root 2 alpha by z by alpha. This choice tells me every time you see an x within the integral, you get an extra factor of root 2 by alpha. So how many factors of root 2 by alpha will you get here? How many factors of root 2 by alpha will you get out? The power how much? Three. Of course, 2 from the powers of x, 1 from the dx. Right? The only thing left is to calculate what this integral is. How much is this integral? Root pi by 2. So you are saying this integral is root pi by 2. By 2 meaning, I'm assuming what you are saying is this. Does everybody here know how to calculate these integrals quickly? There are several ways, of course, of evaluating these, either by using the gamma function version or by using tricks like differentiation under the integral sign. All of these are known, right? Are all of these things known? Anyway, that's the numerator. The denominator we have already calculated before. Root pi by 2. Yes. Okay. I hope the value you have given me is correct. But now that you have this, you can easily calculate the result. What is very important here is that you should be able to make your calculation life easier by grouping the factors together properly. Like say you have a root 2 by alpha here, you have a root 2 by alpha whole cube here. Don't bother opening this out too soon because cancellations will happen after that you open this out. That is, you cancel the root 2 by alpha factor, then you get a square, then you get 2 by alpha square. Use that. Anyway, what you will have at the end of the day is some constant by alpha. And I'm not telling you what that constant is because that's something you can easily calculate just by cancelling out the appropriate factors. The only other thing that I will tell you is when you're calculating the kinetic energy part, there is a simplification which sometimes, there's a trick which sometimes helps you simplify the thing. This, of course, is 1 by twice m. Right? And since P is a Hermitian operator, you can always write this as P psi normed with P psi. Or basically this is what you're doing, right? Psi star d2 psi dx2. What this formula actually tells you is that this is the same as h cross square by twice m. Okay, you could either say that this is equal to this simply by using the fact that this is really psi p acting on p psi, right? That's what this really is. And because p is a Hermitian operator, that's the same as p psi on p psi. That's just using Hermitianity of p. And at a more elementary level, you could just say that this is equal to this because of what? How do you get from here to here? So what's the method which allows you to show that this is the same as this?
Integration by parts.
Integration by parts, exactly. And the fact that when you integrate by parts, taking d2 psi dx2 as your what do you call? I always keep on confusing which one is the first, which one is the second function in nomenclature. But d2 psi dx2 as the second function, I guess, which the one which you integrate, and psi star as the function which you differentiate. Then you get an integrated out part in the integration by parts formula, which will vanish because your wave functions die out fast enough at infinity. But what is the connection between that statement and this one? Here this works because P is Hermitian, right? And here the integration by parts will give you this is the same as this, simply because the integrated out term, which is really psi star times d psi dx. So what this integral part will tell you is that the left hand side is equal to this term plus this term. And then you claim that because the wave function vanishes rapidly enough at infinity, this term will be 0. So this will go away. Okay. But on the other hand, here we made no such statement. All we said was momentum is a Hermitian operator. So that's it. So basically, because for any operator, what happens is psi a phi, or which is really psi acting on the state a phi. That's what psi a phi really means. Is the same as a dagger psi overlap with phi. That actually is how a dagger is defined. And because the operator is Hermitian, a dagger is the same as a, at least as far as this overlap is concerned. So you get a psi phi. So what you're really saying is you just use a Hermitian into a p here. In deriving the psi t psi is the same as 1 by twice m times p psi p psi. But that's exactly what this is in the language of wave functions, right? Because p psi is simply, in the position representation, p psi is simply h cross by I d psi dx. So p psi is overlap with p psi is just a mod square of this quantity that gives you the h cross square up here, and d psi dx mod square. Of course, the 1 by 2m was already there outside. So my question to you is, what is the connection between the two scenarios? Yes? Do you realize what my question really is? In the other way of doing this, all I have done is use integration by parts, right? And the other method is demanding that the momentum is Hermitian. How come the two methods give you the same answer? Because they are two different things, right?
H cross by I ddx is Hermitian.
Uh, is there a question or a statement?
No, sir. For this, it happens.
For which what happens?
As H cross by I ddx Hermitian, so it size
Yeah, but
star
I
del square.
think you are right in what you're trying to say, but I'm confused whether you are really using it being Hermitian as an argument, or my question is I did not use anything like Hermitian. Right? All I used was intuition by parts. That's it. That's all I used. So how is that connected to this one, to the Hermitianity? Okay. DGX is anti-Hermitian because of the two endpoint, the values of this IDX is the same. If this had not been, then the case DDX would not have been anti-Hermitian and P not Hermitian. That is the exact answer. That's the connection between the two statements. Actually, the Hermitian conjugate DDX is Hermitian conjugate of minus DDX is actually not right. It's not true in general. Or the momentum operator H cross by I DDX is Hermitian. That's actually not a correct statement. Or it's an incomplete statement. The important thing is, yeah, the important thing is not just for normalizable states. The basic idea really is this. If you want H cross by I ddx to be Hermitian, that is, what you want is that it should be able to act on both psi star or psi, and you should get the same result in both cases. That is, you are demanding this. Of course, these two are also connected by an integration by parts, something I've done a long time ago. The only important thing is there is an extra piece here as well. The extra piece is and well, in general, what Harshela said is actually more precise in the sense that in general the integral does not even have to be from minus infinity to plus infinity. It could be from some lower limit of your x to some upper limit. Your system may be defined only between a and b. So then this integral would have to be at a and b. And if you want your wave function, your momentum operator to be Hermitian, what you have to demand is this. Psi star psi at b must equal psi star psi at a. Two distinct ways of achieving that. One of them is demanding that the wave function has to die out at the two ends. And the other one is to demand that the wave function be periodic. That is, psi at b be the same as psi at a. So this actually tells you why you see those two boundary conditions. One of them has no real name simply because that's the one which is more common anyway. The wave function vanishes infinitely far away. That's what follows from normalizability. But basically, you're claiming that the wave function vanishes infinitely far away. That ensures that this integrated out term is zero. And the other one is this. This is something which you will encounter very, very often in many physical situations. But the reason why you actually demand periodic boundary condition is not because it's convenient or because of some story that it makes the system look infinite or whatever. The reason why you demand periodic boundary conditions is that that is what you need to make your momentum operator Hermitian. So dead wall boundary condition would also achieve that. The wave function vanishes at the two ends. Or which is the standard normalizability condition if your system is infinitely big, from minus infinity to plus infinity. Just hold on. Okay. So the point is the Hermitianity of P, which I used here, and the vanishing of the integrated out part, which I used here, are actually connected to each other. If this did not happen, if one of them did not happen, the other wouldn't have also worked. They're not two independent arguments. The integrated out part vanishing and the Hermitian and the momentum being Hermitian are actually the same thing. At least for in this particular context. Anyway, I'm not completing the full calculation. You can easily. Okay, by the way, why is this useful? I made a hue and cry about showing you a trick here. The shy can be calculated this way or by doing this. Why is this useful? The answer is simply you don't need to calculate two derivatives, just one will be enough. You calculate the first derivative, take its mod square, and you do a calculation with that. Is this always useful? The answer is no. Sometimes calculating the second derivative and using psi star d2 psi dx2 will be easier to do. So don't blindly mug up either this one or this one. Depending on what your first derivative looks like, differentiating again may be a pain. So using this may help you a lot. But your first derivative is a simple enough function. Differentiating once again might make it even easier to handle. So this is whether this is more useful, the left-hand side or this one, that very often depends on the particular problem at hand. So my advice is keep your eyes open. Try to figure out which one will be easier for you to work out. Okay? Either way, once you finish the calculation, you'll get E alpha of this form. I'm not going to tell you what it is going to be because that's a homework, but anyway. You will get B by alpha from the potential energy, the one which you saw already, and you'll get A alpha from the kinetic energy piece. Now, this is a classic case of a problem where you can actually find the minimum of E alpha without even doing any calculation or without using calculus, to be more precise. Of course, you have to do a calculation. So this hinges upon the fact that alpha plus 1 by alpha, for example, is right. So now you have a perfect square plus a constant which is independent of alpha. So this one will actually be minimum only when root alpha is exactly equal to 1 by root alpha. That is, alpha is equal to 1 basically. And the minimum value is 2. Of course, here the calculation will be different because of the presence of the constants A and B, but you should be able to get that answer without using any calculus. And you will find that the minimum value for E alpha will work out to be half h cross omega. Should not come as a surprise is because we have chosen a family of wave functions which already contains the exact solution. Okay? Very often, the family of wave functions will not contain the exact solution. So what this method will do is within that family, it will allow you to get to as close to E0 as possible. Okay? Now, there are some guidelines to what is a good family to choose. For example, if I choose a family which looks completely unlike what you expect your wave function to be like, then it's almost certain that your answer will be definitely more than E0, but it will be very far from E0. But if you choose a reasonably good class of wave functions, good meaning something which physically resembles what you expect a wave function to have, then you would actually get pretty close to the actual answer. Now, there are techniques for estimating how close you are, or getting some kind of lower bound as well. That is, this one gives you an upper bound. If you also had a lower bound, that would be great, because then you would know that you have sandwiched the exact energy eigenfunction somewhere in between. I will describe some of those things either in the next lecture, or maybe if I find time in a recorded video in between. However, this is basically the procedure that you have to follow. We will see a few examples of this at work, which will be less trivial than this one. But before we do that, can anybody tell me this? Suppose I wanted to estimate the first excited state. Okay. Okay, Sharon is saying, is it not valid to let alpha negative? Yeah. But root alpha equal to 1 by root alpha does not allow you to get alpha equal to -1. That only allows you to get alpha equal to 1. Of course, you could have written this as written alpha plus 1 by alpha as root alpha plus 1 by root alpha minus 2, whole square minus 2. That would have given you a bound of -2. Okay, but you already know that the minimum cannot go below 0, below +2. So a bound of -2 would be bad. X plus 1 by x is a local minima, but not a global minima. Are you sure? That sounds strange.
For negative values, it is negative. And it actually tends to negative infinity when x
Yeah,
tends to
but root
-1.
alpha can always be can only be positive, right? Oh, you mean this one?
Yes, sir.
Oh, well, there I think you will have to excuse my choice. I actually chose alpha to be positive already before. I think you should be able to figure out where. Can anybody tell me in this whole calculation, where did I choose alpha to be positive?
So carrying out the Gaussian integral, is that it?
Here, if alpha had been negative, okay, would these limits have been -infinity to +infinity? Okay, that's a very important point, really. Thanks for pointing that out. This is something which we do unconsciously very often. What Sharon is trying to point out is that we wrote our wave function with x square by alpha square. So that, of course, allowed alpha to be both positive and negative. And I should admit that I had also fallen in the same trap without even thinking. I already assumed that alpha is positive, so I kept on doing the calculation that way. But so this integral, it is a -2x square by alpha square. By the way, this answer root over 2 pi by alpha. Can it be correct even for a negative alpha? Can anybody tell me that? So Shahan has got it, but I'm asking about other people. First of all, this statement that I've made, is this correct for all values of alpha? So this definitely is correct for alpha equal to 1. At least we know what the value is for that. But what about alpha equal to -1? Is the statement correct for that? Yeah, Abir is saying the integral, of course, is non-negative, right? It's definitely greater than equal to 0. In fact, it is greater than 0. Has to be. The integrand is positive throughout, so the integral is definitely greater than 0. So for alpha equal to -1, this formula simply cannot be correct. So where did we slip up there? Of course, the reason why we did not really slip up, at least I didn't think we had slipped up, is because I'd already assumed alpha to be positive from the very beginning. But where exactly did we assume alpha to be positive? All we did was a substitution of variables, right? And this is a perfectly valid substitution which you can carry out even when alpha is negative, can't you? Yes or no? This substitution, root 2x by alpha is z, is a perfectly legitimate substitution to do. Even if alpha is negative, I can still do that. I can't do it only for alpha equal to 0, but let's leave that singular case out. Yeah, Rahul and Harshal are both correct. The fact that we kept the limits unchanged, minus infinity stays minus infinity, plus infinity stays plus infinity. There we had assumed that root 2 by alpha is a positive factor, right? So actually what would have happened is that if we had done this for general alpha, then if alpha is positive, then no problem. But if alpha is negative, the whole thing will change sign. So what you really have is this. That's the actual value for the integral. Not root 2 by alpha, but root 2 by mod alpha. And that of course takes care of the fact that that the integral is of course always non-negative. Root 2 pi by mod alpha is of course always positive. No problem with that. Clear? So this is the important point. Sometimes when we do substitutions, we tend to forget about these things, or especially alpha square root is mod alpha by definition, because I always take the positive square root, but I should not call it alpha unless I have already specified that alpha is positive. Okay. So in this calculation throughout, we have taken alpha to be positive. And that is why alpha plus 1 by alpha really has the minimum at alpha equal to 1. That is the global minimum, not just a local minimum. So is this okay with everybody? So that was really not an intended learning experience right now, but it's an important experience anyway. But the final thing that I will ask you is how, if I wanted to get the first exercise state or estimate the first exercise state, how would you do that using the same method? Let me just remind you that this is what expression value came out to be. So this is definitely what we did was we argued that this has to be greater than or equal to E0. How can we ensure that instead of E0, the bound is E1? Of course, the fact that this is greater than or equal to E0 told us that if I take a family of wave functions such that and within that family of wave functions, I minimize the energy. Okay, Aniruddha has actually an answer to this. Aniruddha says set C0 equals 0. If we had some kind of magic wand which allowed us to do that, then this term will go away. Then this will be greater than or equal to E1. I'm not going to repeat the rest of the calculation because I know everybody should be able to figure that out, right? Because now the normalization condition, if C0 is 0, sorry, the normalization condition would be C1 mod square plus C2 mod square, etc. adds up to 1. And now if in this sum I replace all the E's by E1, remember E1 is the lowest one which is in the sum right now. So if I were to replace all the E's by E1, I'm going to bring the sum down, the same argument that we had before. The only other thing that I can tell you about here is, of course, if C0 is 0, it's fine. But how do I do that? Or one way to understand how, or rather at least try to get a handle on how, is this. Can you restate this demand in terms of something which sounds more quantum mechanical? Unfortunately, that's the best I can do right now as a hint. C0 equals 0. What does that imply about the wave function psi? Or the relationship between the wave function psi and the energy eigenfunction phi 0. Can we subtract the psi 0 part from psi? Would be great if we could. But how do we do that? Or how do we... Okay, I think that's one way of handling this. But the basic idea is, first of all this, if C0 is 0, what does it tell you about the relationship between psi and phi 0? Kurbawal is saying probability of finding ground state eigenfunction is 0 when psi is acted upon by it. Psi is acted upon by it is really... Psi does not act upon anything, by the way. So, Kurbawal, I would urge you to think about your language here a bit, because this might be simply a mistake in what you have typed, or it might simply be a mistake in your understanding. If the latter, then it's really problematic. So I would ask you to think about it first and then discuss it later. Okay? Now, I'm not saying it's opposite or anything. I'm just saying H acting upon psi, etc. is really even physically wrong in this case. Okay, Shayan and Shashank has actually given us the right answer. This C0 simply means or, which actually is psi is orthogonal to the ground state wave function. Now, this gives us some kind of handle on the problem in the sense that if I already know the ground state eigenfunction, sometimes I know the exact ground state eigenfunction. For the harmonic oscillator, of course we do. For the problem that we had, e to the minus alpha x to the 4 was the exact ground state eigenfunction. For this, making psi orthogonal to phi 0 is simple. You just, you just put that as an additional condition, perhaps. Integral of psi star phi 0 dx is 0. So you solve the problem subject to this particular constraint, that the integral of psi star phi 0 is 0. Okay? Clear? However, there are situations like, say, if the potential is, suppose your potential is alpha x square plus beta x to the 4. A quartic potential which you don't know the exact solution to. So you don't even know the ground state wave function. But I'm claiming that you can ensure that the wave function is orthogonal to the ground state even if you don't know the ground state wave function here. Can anybody tell me how? So for this potential, we don't know the exact ground state. Phi 0 is not known exactly. But my claim is, even despite that, you can find out a condition, or find out a way to ensure that psi is orthogonal to phi 0. Can anybody tell me how? The answer is very, very simple. Let me just give you that as a hint. Any idea how? Yes? Yeah, Shayan said choose an odd function as a trial. Well, in this case, we know that, okay, from the theorems, etc., that we have studied already in the preliminary lectures, we know that the wave functions have to be even and odd respectively, and the ground state being nodeless has to be even. Remember, an odd function always has a node at x equal to 0. The ground state is an even function. So if you choose an odd function as a trial state, so some odd function with parameters, or some arbitrary parameters which you can work with, then you have ensured that whatever you have chosen is orthogonal to the ground state. So if you use such a trial family, then minimizing with respect to that is going to give you the ground state, not the ground state energy as a lower bound, but the first excited state energy as a lower bound. There's one warning before anybody asks. Some of you should definitely have asked this question by now. Minimizing gets you closest to the energy eigenfunction, or to the ground state energy, or in this case, the excited state energy, first excited state energy. But how close? That is, after all, the 10th excited state energy is also more than E0, right? So the lowering might get you to E10 and not to E0. And the answer is, if you have not chosen your family of wave functions wisely, you will end up at a very, very high energy, way beyond E0. So this is a bit of art as well as science. You have to be, well, it's more science than art really, but you can't just start blindly and choose a family of wave functions. You have to use whatever you know about the system and what kind of wave functions a system like this should have. And this is precisely why exact solutions are important. In situations where you know the exact solution, you can study their properties and figure out what kind of general things that will happen, even in other problems, and use those here. So we will go on and talk about more details of this variational method in the coming lectures. But this is a very important thing anyway. Okay. So I'm done for the day, but if you have any questions, please ask. If not, okay, if nobody has any questions, we can fold up. Nobody has any questions. Right. Okay, anyway, bye for today. Remember the class test on Friday.